Alright, we just did the sine rule. Let's talk about another rule generally to do with general triangles. Okay, so again we have our angle B and A, sides B and A, right, so they go in opposite pairs, C and C. This time I'm going to add a C in. Capital C and small c look the same. Okay, and we're going to find another relation that's kind of cool with all triangles. And this you can get by, again, you have this, you consider the height of the triangle. And now we're going to use Pythagoras Theorem twice here. Because now we do that thing where we split it into two right angle triangles. And I'm also going to introduce this variable x. Now just note that when I project b onto the base here, that x is just equal to b cos a. So it's really just a placeholder for this variable here. So keep that in mind. Now when I use Pythagoras' theorem twice, let's use it in the left triangle. So I get x squared plus h squared equals b squared. Well, okay, with where that comes from, right? Just, the free lengths of the sides. And then this other right angle triangle, notice it's not C because C is the entire base. I need to take away x if I want the base of that right angle triangle. So C minus x, so that refers to this part here. So C minus x squared plus h squared equals a squared. Alright, so let's eliminate h from these two equations just by subtracting one away from the other. Now, which way do I want to do that? It doesn't really matter. Let's take this one, so this is equation 1, and I'm going to subtract equation 2. So 1 take away 2. Notice expanding out these square brackets, that's just c squared minus 2cx plus x squared. Okay. And therefore, when I do the subtraction, what do I get? Well, I'll get c squared minus 2cx, this is equal to a squared minus b squared. Okay, so let's move the b squared over to the other side so it becomes added, and let's replace x with what it was up here. We said it was b cos a. That's what x is equal to, b cos a. So then we get the rule, right? So the rule says a squared is equal to b squared plus c squared minus 2bc cos a. Okay, if that seems too fast, just go back and play the video at 50% speed. No, I'm kidding. Just go back, watch it a few times, follow your algebra, and you should arrive at this rule, right? This will also work when we're dealing with a triangle where b isn't obtuse, right? Where there's the other set of triangles that you need to consider as well. So for completeness, as an exercise, you might want to prove it for triangles of this nature. It's very, very similar. Okay, so here's the angle B, and we have the dashed line coming down here representing H. And this time X will sort of be, you'll define that as a length here. And really X is, you write that in terms of the projection of some other thing, and we just end up getting the same result. So you can show that this rule is true for all triangles. So a squared is b squared plus c squared minus 2bc cos a. It's used quite a lot. It's really important to know. It's also, either you use it to find the length of a side, right? So, imagine we have a scenario such as this for 6, and I want to know this side, let's call it x, and I have this angle being like, I don't know, 40 degrees or something. Then I can get x, so x would be my a, and I'd plug all the numbers into the right hand side, and I'll find a solution. I'll walk you through a few examples in the other video, in the next video in the series. Or we could use it in another way. So if we want to find an angle, so let's say we knew this was, I don't know, let's say 8, but I don't know what this angle is now, then that would be like my a. And actually it's almost easier to remember another version of this rule, because I want to make cos a the subject here, so I'm just going to do that. And sometimes we call this the cosine rule in reverse. So let's move all of this, let's move this entire term over to the left, and then I'll get the a squared and I'll move it over to the right. Let's write it in orange. And then I'll divide by 2bc. So I'm going to do all this in one go. It might look a bit of a jump, but okay. Equals b squared plus c squared minus a squared. And then I'm going to divide that by 2bc. And the 2bc came from where it was. It came from up here, remember? Because it was part of that term. So there it is. And I've just swapped this term with the a squared. So I've got this relation, and this is kind of the cosine rule in reverse. And it's used to find an angle when you have all three sides. It's the same rule though. So again, looking at the proof, it wasn't really that hard. We just kind of, turned a general triangle into two right angle triangles, and then used Pythagoras Theorem twice, right? And we were able to compare all the squared things, eliminate the dummy variable h, and then we could get a relation with the cosine, right? So h would be, you'd only introduce h if you're looking for some sort of sine rule relation, if you want to keep it in there. But in this case, we wanted a cosine rule relation, which is why we had our variable x, and we eventually got the equation where we left it in. Okay.